Welcome to the Deep Dive, where we cut through the information overload to bring you the most fascinating insights from complex topics. Today, we're your guides to a really fundamental chapter from Shriver Atkins Inorganic Chemistry, the 5th edition. We're doing a deep dive into the alkali metals. Our mission here is pretty simple. Make this cornerstone of inorganic chemistry clear, maybe even engaging, and definitely memorable. And all without needing any visuals. We're going to try and uncover not just what these elements do, but why they behave the way they do. And we'll put a special focus on lithium because it's surprisingly unique.
That's right. You'll see pretty quickly that these group 1 elements, the alkali metals, well, they are metallic, but they're also unusually light and incredibly reactive. We'll explore their striking similarities, the really clear trends you see as you move down the group, and yeah, those fascinating anomalies, especially with lithium. The goal is to kind of connect the dots for you so you grasp the bigger picture.
So if you're a college student, maybe trying to get a handle on inorganic chemistry, or honestly, just someone curious about the basic building blocks of our world, you're definitely in the right place. Let's jump right in.
Okay, so to kick us off, who exactly are the alkali metals?
Right. We're talking about lithium, sodium, potassium, rubidium, and caesium.
And we're skipping francium today.
Yeah, we'll set francium aside. It's highly radioactive, exists in really tiny amounts, so it's not typically discussed in the same detail.
Got it. So these are all metals, but you said they're not like typical metals, not hard and dense.
Exactly. And the key to understanding these elements comes right down to their electron setup. They've all got just one valence electron, that NS1 configuration.
Just one electron on the outside.
Just one. And that single electron dictates so much. Physically, yeah, they're excellent conductors of electricity and heat like metals should be, but they're also remarkably soft.
Yeah.
You can literally cut most of them with a knife.
And they have surprisingly low melting points, which actually decreases as you go down the group. Caesium, for instance, melts at just 29 degrees C.
29 degrees. So you could, theoretically, melt caesium in your hand on a hot day. Though, obviously, don't do that.
Please don't. But yeah, theoretically. And what makes them so soft? Well, it's all about weak metallic bonding. Since each atom only contributes that one electron to the metallic bond, it's just not a very strong attraction holding the atoms together.
Makes sense.
Plus, they all adopt what's called a body-centered cubic, or BCC, structure. If you picture it, each atom is at the center of a cube made by 8 other atoms. It's a relatively open packing arrangement, not close packed like many other metals. Combine that open structure with their large atomic sizes, and you get incredibly low densities. Lithium, for example, is less than half the density of water. It floats.
Which is pretty counterintuitive for a metal. And visually, I remember these from Chem Lab. The flame tests are spectacular.
Oh, definitely. Classic identifiers. You get that beautiful crimson red for lithium.
And that really intense yellow for sodium. Streetlights.
Exactly. Potassium gives a sort of lilac red to violet color. Rubidium is more violet, and caesium gives off a lovely blue.
It's like a chemical rainbow.
Yeah.
And labs use this, right? With instruments like flame photometers.
Precisely. For quantitative measurement, absolutely. It's a direct way to see how much is there. Now, chemically, their properties are tightly linked to their atomic radii, the size of the atoms, and these radii steadily increase as you go down the group.
Bigger atoms as you go down.
Bigger atoms, which means that single valence electron gets further and further away from the nucleus.
Okay.
And that translates directly into a decrease in their first ionization energy.
Meaning it takes less energy to remove that outer electron.
Exactly. Put simply, it just gets easier and easier to pluck off that electron as you go down the group.
And when something loses an electron easily, that means it's highly reactive.
Precisely. Because those ionization energies are so low, these metals are incredibly eager, you could say, to lose that electron and form a positive ion, and may ion. And this reactivity, it increases dramatically as you descend the group.
Which brings us to what I always found the most, dramatic part. Their reaction with water.
Yeah.
It really scales up.
Oh, it does. It's quite the spectacle.
Lithium reacts, fairly gently. It fizzes. Sodium reacts much more vigorously, zipping around the surface.
Melts into a little ball.
Yeah. Then potassium catches fire. It basically explodes.
Often with that characteristic lilac flame, yeah.
And rubidium and caesium, just boom, explosive ignition, right?
Instantaneously, yes. And part of the reason rubidium and caesium are so violent is, as you hinted before, they're denser than water.
So they sink.
They sink below the surface, which contains the heat and hydrogen gas produced, leading to an even more intense contained explosion. It's quite dangerous. Now, thinking about the Y, again, their standard potentials, which measure how easily they lose electrons in water, are all very large and negative, around negative 3.0 volts.
Very negative, meaning very easy to oxidize.
Exactly, consistently confirming that strong tendency to be easily oxidized. But what's intriguing, maybe a bit surprising, is that these potentials are remarkably uniform across the whole group, despite that escalating visual drama we just talked about.
Wait, so the energy involved doesn't change much, even though potassium explodes and lithium just fizzes. How does that work?
It highlights this delicate balancing act in the thermodynamics. We can think about it using a sort of Born-Haber cycle approach for the process in solution. As you go down the group, yes, it takes less energy to turn the solid metal into gas atoms, sublimation, and less energy to remove the electron, ionization. Both those trends make oxidation easier.
Okay, that makes sense for increasing reactivity.
But the energy you get back when the resulting positive ion gets surrounded by water molecules, the hydration enthalpy that becomes less favorable for the larger ion, bigger ions don't interact as strongly with water.
Ah. So the factors pushing for more reactivity are counteracted by the hydration energy becoming weaker.
Exactly. These opposing forces roughly balance out, leading to those surprisingly similar standard potentials.
So the overall thermodynamic drive is similar, but the kinetics, how fast it happens, and things like melting point and density
Yeah.
change the visual outcome drastically.
Precisely. It's a fantastic example of the difference between how energetically favorable a reaction is and how quickly it actually proceeds under certain conditions.
And because they're all so reactive, especially with air and moisture, you have to store them carefully.
Absolutely. Usually under hydrocarbon oil or kerosene to prevent them from reacting with atmospheric oxygen and water vapor. Though you can handle lithium, sodium, and potassium briefly in dry air, but rubidium and caesium tarnish almost instantly.
Okay, that extreme reactivity is fascinating, and it must dictate how they behave when they actually form compounds. You mentioned ionic bonding.
Overwhelmingly, yes. Their chemistry is dominated by forming the amyl ion. Take their hydrides, for instance. They readily form ionic hydrides containing the IO anion, the hydride ion. These are typically white solids, often adopting the familiar rock-salt structure. Sodium hydride, NaH, is a great example, very useful in organic synthesis as a strong base that isn't a nucleophile, but they react violently with water, releasing hydrogen gas.
Okay, and they're halides, like sodium chloride, table salt.
Yep, MX compounds. Most of them, like NaCl, also have that rock salt structure, which is a 6 central 6 coordinate setup. Each ion is surrounded by 6 ions of the opposite charge. But because cesium ions are so much larger, cesium chloride, cesium bromide, and cesium iodide switch to a different structure, the cesium chloride structure. It's an 8-on-8 coordination. It's all about how efficiently ions of different sizes compact together.
Interesting how size dictates the crystal structure. What about reactions with oxygen? You mentioned they have to be kept away from air. What happens if they do react?
It's quite varied, and again, size plays a role. Lithium, the smallest, forms the normal oxide, LiO, containing the O ion.
Just the simple oxide.
Right. Sodium, being a bit larger, primarily forms the peroxide, no-ero, which has the O ion.
Okay, peroxide, like hydrogen peroxide, but with sodium.
Sort of, yeah, it contains that same peroxide dianion. And then the heavier elements, potassium, rubidium, and caesium, they go a step further and form superoxides, M-ero, containing the O-aerobetical anion.
Oxide, peroxide, superoxide. Why the difference?
It's a great example of lattice energy effects. Larger cations are better at stabilizing larger, more diffuse anions. The oxide iron OO is relatively small. The peroxide OO and especially the superoxide OO anions are larger. So as you go down the group, the larger co-arbo and cesions provide a better energetic match, a more stable crystal lattice for these larger anions compared to the simple oxide.
So bigger cations stabilize bigger anions better in the solid state.
Got it. And these oxides, are they acidic or basic? Oh, definitely basic. They all react with water to form the corresponding hydroxides, releasing heat. Potassium superoxide, KO, actually has a really neat application.
Oh.
It's used in self-contained breathing apparatus, like for firefighters or in submarines. It reacts with the CO you exhale and releases fresh oxygen.
Wow, that's clever chemistry. 2K euro plus 2C euro gives 2K euro plus O.
Right.
Wait, no, that's not balanced. It reacts with water vapor and co-euro to produce oxygen and potassium carbonate, hydrogen carbonate. That's incredibly useful.
It is. Lithium peroxide, LiOO, is sometimes used in aerospace for similar reasons,
Yeah.
mainly because lithium is so light.
Okay, let's talk about the hydroxides themselves, like NOH.
Right, the alkali metal hydroxides, MOH, they're typically white crystalline solids, very soluble in water, except maybe lithium hydroxide, which is less so, and they are deliquescent.
Meaning they absorb moisture from the air and can eventually dissolve in it.
Exactly. They also readily absorb carbon dioxide from the air, forming carbonates. Lithium hydroxide actually forms a stable hydrate, LiOH, sometimes written as LiOH8HO based on older texts, but the monohydrate is common. And sodium hydroxide, NaOH caustic soda, is a huge industrial chemical made by the chloralkali process, used in making soap, paper, aluminum, and countless other things. Even drain cleaner because it dissolves grease and hair.
Okay, massive industrial importance. Now, what about compounds with oxoacids, things like carbonates?
Good question. The carbonates are interesting because generally group 1 elements form the only common soluble carbonates. Most other metal carbonates are insoluble.
Ah, that's a key point. Except, wasn't lithium carbonate different again?
You remembered, yes, lithium carbonate LiCS is the exception. It's only sparingly soluble.
Why? Is it that small lithium ion again?
It is indeed. That small size and high charge density of lithium mean it has a higher polarizing power. It distorts the electron cloud of the large carbonate anion, leading to more covalent character in the bond. And energetically, the lattice energy of LiCoy isn't as favorable compared to its hydration energy as it is for, say, sodium carbonate. Plus, larger cations generally stabilize larger anions like carbonate better in the solid state.
This keeps coming up, lithium being the odd one out due to its size.
It's a major theme. This size difference also shows up in thermal stability. Lithium carbonate decomposes to the oxide and co-zero at a relatively low 650 degrees C.
Whereas the others are more stable.
Much more. Sodium carbonate melts above 800 degrees C before decomposing, and rubidium carbonate is stable up to nearly 1,000 degrees C. Again, the larger cations provide greater stability to the large carbonate anion.
Fascinating trend. And sodium carbonate, soda ash, that's another big industrial chemical, right? Used in glass?
Huge. Glass manufacturing, water softening, making other chemicals. It's produced mainly by the Solvay process, which is quite an ingenious cycle using salt water, ammonia, and calcium carbonate as raw materials.
Right. Bubbling CoOs through ammoniated brine precipitates sodium hydrogen carbonate.
Which is less soluble, NaHCO, that's baking soda. Then you heat the NaHCO to get NiOSha.
And baking soda itself, NaHCO, it releases co-euros when heated or reacted with acid, hence its use in baking and some fire extinguishers.
Precisely. Other important oxysalts include the sulfates, like NiOS Glauber salt, used in detergents and paper production, and the nitrates, NaNO and KNO, historically important as fertilizers and components of gunpowder.
And does lithium nitrate behave differently too?
It does. When you heat lithium nitrate, LiNO it decomposes directly to the oxide, LiOO plus NO and OO. But the other alkali metal nitrates, like potassium nitrate, KNO, first decompose to form the nitrate, KNO, and oxygen. You need much higher temperatures to get them to decompose further to the oxide. Another lithium anomaly.
Okay, lithium really does play by its own rules sometimes. You also mentioned earlier that only lithium forms a nitride and a carbide directly.
That's right, reinforcing its uniqueness. Only lithium reacts directly with nitrogen gas to form lithium nitride, LiEuro, a reddish solid. It's actually a good ionic conductor and has potential for hydrogen storage applications.
And the carbide.
Again, only lithium forms its carbide, LiEuros, directly from the elements. This contains the dicarbide anion. The other alkali metals can form similar dicarbides, amurero, but you typically need to react the metal with ething, acetylene.
But potassium, rubidium, and caesium do something else with carbon, don't they? With graphite.
Ah, yes, the graphite intercalation compounds. Because K, Rb, and Cs are larger, they can actually slide between the layers of graphite sheets. You get compounds like CaK, which are often bronze or blue and are electrically conductive. Lithium also forms an intercalated graphite compound, Li, which is incredibly important as the anode material in most lithium-ion batteries. And related to this are fullerenes, like Kc, derived from Buckminster fullerene, which are superconducting at low temperatures.
From simple salts to superconductors, it's quite a range. Let's loop back quickly to solubility and hydration. We touched on LiCo's being less soluble. Are there general rules?
It's complex, often boiling down to a balance between lattice energy, holding the solid together, and hydration energy, stabilizing ions in water. Generally, salts where the cation and anion are very different in size tend to be more soluble. Hydration energy strongly favors dissolving, especially for the smaller, more charge-dense ions like Liu and Neo. That's why they often form stable hydrated salts, like the LiOH monohydrate we mentioned, or now SeO10UO.
All right, the water molecules stabilizing the small ions. Now, you mentioned those amazing blue solutions in liquid ammonia earlier. Can we dive a bit deeper there?
Absolutely. They are truly remarkable. When you dissolve an alkali metal in liquid ammonia, say sodium, the metal loses its valence electron. In dilute solutions, these electrons become solvated, trapped in cavities formed by ammonia molecules. It's these solvated electrons that absorb light in the red region, making the solution appear a deep, intense blue. They are also paramagnetic because of the unpaired electrons.
Electrons just floating around in solution.
Pretty much. And as you increase the concentration, the solution becomes more concentrated in electrons, interactions increase, and it turns a metallic bronze color, looking and behaving much like a liquid metal, an expanded metal. These solutions are incredibly powerful, reducing agents.
Reducing agents. What do they reduce?
Right. All sorts of things. They're used to make those graphite intercalates, fulleриdes, and also zintal phases we'll touch on. They can reduce aromatic rings in the Birch reduction in organic chemistry. And even more strangely, under the right conditions, using specific complexing agents and other solvents like amines or ethers, you can sometimes force the alkali metal atom to gain an electron, forming an alkali anion. Like Ne.
A negative sodium ion.
Seriously. For example, by using a cryptan ligand to strongly complex the nitrocation, you can isolate salts like Na-cryptan-ano. These are confirmed by their diamagnetism, no unpaired electrons. It shows the incredible power of solvation and complexation.
Mind blown. Okay, what about the zintal phases you mentioned?
Zintal phases are fascinating compounds formed between highly electropositive alkali, or alkaline earth metals, and more electronegative main group elements, typically from groups 13 to 16, like tin, lead, antimony, bismuth. You can think of them roughly as ionic salts, where the alkali metal has completely transferred its electrons to the main group element, which then forms complex polyanions, clusters, or networks.
So instead of simple ions like clay, you get complex negative clusters.
Exactly. Examples include things like tetrahedral SNO or square pyramidal GO, or even complex structures like GO, which looks like a capped square antiprism. These materials are often semiconductors, brittle, and diamagnetic. They bridge the gap between simple salts and alloys.
Wow. Okay, let's turn to coordination compounds. You said group 1 ions are hard Lewis acids. What does that mean for the complexes they form?
Being hard Lewis acids, especially LiO through Ca, means they prefer to bind to hard Lewis bases, ligands that have donor atoms like oxygen or nitrogen, which are small and not easily polarized. Think water, ammonia, ethers, alcohols. Complexes with simple monodentate ligands, ligands that bind through only one atom, are generally quite weak and usually only exist in solution.
But they can form stable complexes.
Oh yes, especially with chelating ligands, ligands that can grab onto the metal ion with multiple donor atoms. EDTA is a classic example. Even better are macrocyclic ligands like crown ethers and cryptans. These are large organic molecules with central cavities lined with donor atoms, usually oxygen or nitrogen.
Like the 18 crown 6 you mentioned. Fits potassium perfectly.
Exactly like that. 18 crown 6 has a cavity size that's almost a perfect match for the cation. Smaller crown ethers prefer LiO or Na. Larger ones prefer Arbo or CCO. This size selectivity is crucial. Cryptans are even more effective because they encapsulate the ion in 3 dimensions.
Like building a custom cage for the ion.
Precisely. This has huge implications. It's similar to how biological systems use specialized protein channels and carriers, like valinomycin, to selectively transport Na and Ca across cell membranes. And as we saw with the alkalides, using these powerful ligands allows chemists to do extraordinary things, like isolating those sodide salts, Na-cryptan-OMA, or even electrides, where the counteranion is essentially a trapped electron, like CS18 crown 6 here.
An electron is the anion. The chemistry is wild. Okay, finally, let's wrap up with organometallic compounds. Highly reactive, you said.
Extremely reactive, often pyrophoric, catching fire spontaneously in air and violently hydrolyzed by water. They feature direct metal-carbon bonds.
How are they typically made?
Common methods involve reacting the alkali metal with an organic halide, or reacting an existing organometallic compound, like an organomercury compound historically, with the alkali metal in a transmetallation reaction. or deprotonating a sufficiently acidic organic compound using the metal or a strong base like NaH.
And are they all equally important?
Not really. By far the most important are the organolithium compounds, things like butyllithium,
Yeah.
butyl. They are incredibly useful reagents in organic synthesis. Unlike the organometallics of the heavier alkali metals, which are often highly ionic and insoluble, organolithiums tend to be liquids or low-melting solids, soluble in hydrocarbons, and surprisingly thermally stable, but still very reactive.
Why are they so different? More covalent character again.
Exactly. The small size and relatively higher electronegativity of lithium compared to the others leads to significantly more covalent character in the Lysine bond. They also have fascinating structures. They don't usually exist as simple monomers but form aggregates clusters like tetramers, LAR, or hexamers, LAR, held together by electron-deficient multicenter bonds. The exact structure often depends on the R group and the solvent.
So, complex structures. But what makes them so useful in synthesis?
Two main things. They are excellent nucleophiles. They readily attack electron pore centers to form new carbon-carbon bonds. And strong bases, they can remove protons from even weakly acidic organic molecules. This makes them invaluable for making more complex organic molecules, converting p-block halides into other organoelement compounds, initiating certain types of polymerization reactions, like for synthetic rubber, and they're absolutely crucial in the synthesis of many pharmaceuticals.
And you can fine-tune their reactivity.
Yes. For example, adding chelating ligands like T-meta tetramethyllethylenediamine can break up the aggregates and make the organolithium reagent even more reactive by coordinating to the lithium and making the carbanion effectively bearer.
Well, we've certainly covered a huge amount of ground in this deep dive into the alkali metals. It's amazing how you go from their, seemingly simple metallic nature at the start through all these trends, reactions, complex compounds, and specialized uses. It really drives home the versatility of these group 1 elements, and especially that persistent, unique character of lithium compared to its heavier relatives.
It is quite remarkable, and what's truly fascinating, I think, is how well the predictable trends based on atomic size, ionic size, ionization energies explain so much of their behavior. That simple ionic model, maybe tweaked for lithium's covalent character, gives you powerful insights into their bonding, structure, and properties. And understanding these fundamentals directly connects to why they have the specific, sometimes surprising applications they do, from batteries to medicine to industrial processes.
So, thinking about all this, what's maybe one thing you'd want our listeners to mull over after this deep dive? Considering that delicate balance we saw between the fundamental chemical principles and the very specific, sometimes unusual applications, where might new, maybe entirely unexpected uses for these simple alkali metals be discovered next? Could it be by deliberately tuning those atypical behaviors, like the ones we see with lithium?
That's a great question to ponder. It really encourages you to think about that interplay of size, charge, and the chemical environment, how subtle changes in ligands or solvents, for instance, can dramatically alter properties and potentially lead to entirely new functions or materials. Thinking about how those core principles can be manipulated is where discovery often happens.
Absolutely. Well, thank you so much for joining us on this deep dive into the alkali metals. We really hope you found it as illuminating and maybe even exciting as we did. And with that, from all of us here at the Deep Dive and the Last Minute Lecture team, thank you for listening and keep exploring.